Okay, so we've got two kinds of energy we're dealing with here. Potential energy and kinetic energy. Potential energy is stored energy. Whereas kinetic energy is energy of motion. The abbreviations we use for potential energy are P sub E, and for kinetic energy, it's K sub E. The equation we use for potential energy is mgh. For kinetic energy, it's 1/2 mv squared. And m is the mass of your patient. And g is acceleration of gravity. And h is the height fallen. And unit-wise, this is going to be in kilograms as the mass, acceleration is always in meters per second squared, and the height is always going to be in meters. Now for kinetic energy, m is the same, still mass in kilograms, and v is velocity, basically it's speed, and the units for that are meters per second. Okay, so let's take a look at a concrete example here. Let's say our guy, here's our guy, and he falls straight down, and this distance, delta d, is 30 feet, which is approximately equal to 10 meters, roughly. Okay, so the guy falls 3 stories down. Well, at the top, when he's starting to fall, all his energy is potential energy. At the bottom, when he hits the bottom, all the energy is kinetic energy. This means that these two energies must be equal. So he starts off with all potential, and he ends up with all kinetic the instant he hits the ground. So if we put those two equations together, if we make them equal, we can actually calculate how quickly his speed at which he hits the ground. Okay, so that's what we're going to do. We're going to do potential energy is equal to kinetic energy. That means that mgh is equal to 1/2 mv squared. If you want, what we can do is we can cancel out to make our math a little bit easier. It really doesn't matter how much he weighs, what his mass is. So now we're left with gh is equal to 1/2 v squared. Well, we know acceleration due to gravity. We know the height. We don't know the speed at which he hits the ground, but we can calculate that out. So let's isolate v. So you get 2gh, and if we take the square root of that, that will equal our velocity. So you get 2. By the way, g is approximately 10 meters per second squared, and the height is 10 meters in this case. So v is equal to the square root of 2 times 10 meters per second squared times a height of 10 meters. All right. And that's equal to the square root of 200, which ends up being 14 meters per second, which is roughly equivalent to 31 miles per hour. And that is going to be the speed at which he hits the ground from a height of 30 feet or 10 meters. Now, for you physicsy folks, there's actually another equation we could also use. I don't know if you remember this one from UAM, Uniform Accelerated Motion, and that equation is your final velocity squared is equal to your initial velocity squared plus 2 times acceleration due to gravity times the distance you fell. So we know that his initial velocity when he first started falling is 0. So that means we're left with this. V final squared is equal to 2a delta d. Well, this is the unknown. We know that acceleration due to gravity is 10 meters per second squared, and we know that delta d is 10 meters. So, as Mr. Carapucci would say, let's plug and chug. So you have v final squared is equal to 2 times 10 meters per second squared, roughly, times 10 meters. So v final squared is equal to 200. Looks familiar. That means your final velocity is equal to the square root of 200, which is equal to 14 meters per second, which is equal to 31 miles per hour. So again, this confirms falling from a height of 30 feet, you will be traveling at 31 miles per hour once you hit the ground, neglecting air resistance, of course. So basically, this is the same thing as standing out in the middle of the road and getting hit by a car going 31 miles per hour. Ouch.